In the previous video 6.3, you were introduced to vectors and really the basic vocabulary and skills of working with vectors. For example, you were able to do some computation with vectors such as adding them and finding the resultant of adding two vectors together. Now what we're going to be facing is a challenge situation where you're going to have to apply these skills as you try to process through this challenge. So before we get into that challenge, what I wanted to do was just kind of point out some key objectives that hopefully will tie some certain ideas and concepts together. So I'm not going to list through these key things to watch out for, but we are going to be one at a time approaching each one of these objectives. The first thing that we're going to do is be aware that your calculator interprets angles as standard position angles. So recall your calculator is going to be taking in some sort of angle that you type in, and it's going to regard it as standard position. So in other words, it's going to look at it as an angle that's open counterclockwise from the positive x-axis. So looking through your calculator's eyes, if you were ever to do a sine of 30 degrees, your calculator is looking at 30 degrees as this angle over here, where we open from the 30-degree angle counterclockwise from the positive x-axis. Here is just some more examples of what your calculator would be doing. If you wanted to calculate those hot spots on the unit circle, so those x, y values, you could be doing the cosine of 30 degrees, comma sine of 30 degrees, and what your calculator would do is look at this angle right here, so 30 degrees. Alright, and we would get approximately 0.87, comma 0.5. If you wanted to do 150 degrees, that's over here, and what that was opening from the direction counterclockwise 150 degrees from that x-axis. So that's negative 0.87, comma 0.5. Now keep in mind this is going to be that same reference angle as the 30-degree mark over here. This is 30, this is 30. So you technically could evaluate 30 degrees and then take into account the negativity. But if you just type in cosine of 150 degrees, it's already going to take into account the negativity of going that direction of the magnitude, in these cases 1, since we're on the unit circle. Alright, 210 degrees would be all the way around. Okay, and then another reference angle of 30 right here. And then 330 is going to be all the way around to this point, reference angle 30 here. Okay, so you can see these approximations. We're going to start using decimal forms instead of these exact radical forms. This really showed up at the end of working with that 6.3 assignment that you did. Some of your problems would give you a magnitude and a direction, and it would ask for component form, because a component form is the easiest thing to work with. We like to break it down in terms of an x component and a y component, because we can look at things individually that way. So if you ever were given a direction such as down here, an example of a component form vector v of magnitude 50, direction 150, it would look something like this. Okay, and this is going to be 50. And so what we could do is we could say, well, you know, here's a right triangle, and then here is 150 or reference angle 30. Remember, if you ever wanted the y value, we would use sine. If we ever wanted the x value, we would use cosine. So cosine of 150 degrees is equal to the adjacent, which is this leg touching. We're using that reference angle technically. So this leg touching, the adjacent over hypotenuse, which is 50. So what you would see is this would result, if you solve for that x, multiplying 50 to both sides, it would be 50 cosine of 150 degrees. Alright, if we wanted y, this is the opposite to that reference angle. So we would have to take sine of 150 degrees and then equals and y over 50. So what we would be doing is getting that y component of our component form. So you would end up with getting 50 times sine of 150 degrees. So all in all, this is going to be 50 times cosine of 150 degrees, comma 50 times sine of 150 degrees, but what you can do is start looking at it as just this right here. Okay, so when you do that, you are going to get approximately negative 43.3 comma 25, which means we moved negative 43.3 and up 25 to get to that point right there, which had the overall vector component of a 50-degree magnitude and the direction of 150 degrees. Alright, so we have accomplished objective number 1. Be aware that your calculator interprets angles as standard position angles. Now what we're going to move on is the direction can be calculated, but remember the inverse function ranges. We need to remember that the inverse functions, arc sine and arc tangent, are limited to this half of the unit circle. So in other words, quadrants 1 and 4, whereas arc cosine can be evaluated in the top portion of the unit circle. But what ends up happening is a lot of time we can just use the first reference angle in quadrant 1 to figure out what we're actually looking for. So I did go ahead and in GeoGebra I plugged in the direction of 1, 150 degrees for the vector u. So you can see here's a magnitude of 1, alright, and then it was in the direction of 150 degrees. So up here is the corresponding vector components, the x and the y value. So if you were to look at this right here, it's going to be negative 0.87 and up 0.5. If I wanted to calculate this angle right here, well, you could go ahead and try to do tangent of theta is equal to 0.5 over negative 0.87. But what you're going to get is it actually is going to be evaluating this angle down here. And when you do that, you're going to get, tan inverse, I'm getting ahead of myself, tan inverse of this. What you're going to get is approximately negative 30. So I'm really actually getting this angle down here, negative 30 degrees, and it's because of the restrictions that we addressed when we were studying inverse trig functions. This thing right here is evaluating 0.5 over negative 0.87 as this angle right here, and it's going to be negative because it's moving in the standard position, this time clockwise from our x-axis, so it's going to interpret it as negative 30. So a lot of the times what I would do is I would just look at the positive values, the 0.5 and the 0.87, figure out what that overall reference angle is because it's going to be the same no matter what quadrant you're in. So if you were to calculate that tangent of theta is equal to 0.5 over 0.87, and even if you're over here where they're both negative, or over here where one's negative, one's positive, or down here, just look at it as positive, evaluate the inverse tan, okay, and acknowledge that this is going to be theta is equal to 30 degrees no matter where you are. So the direction can be calculated, but we need to keep in mind the inverse ranges. The next objective is to know that you need to be able to translate the bearings to standard position, and it takes some thought. So let's go ahead and recall that there are two ways that we can notate bearings. We can do a clockwise from north, which would be just written a bearing of 60 degrees is 60 degrees in the clockwise direction of north. So we could go ahead and say, hey, if I wanted to communicate to you that you needed to go in a direction of a bearing of 60 degrees, it would look something like this. Go 60 degrees, clockwise direction. There it is right there. Okay, so there's a bearing of 60 degrees. Another way of doing this is to say we go 60 degrees east of north. So this is actually going to look very similar, but we're going to go in the easterly. Here's east, west, north, south. We're going to go 60 degrees in the easterly direction of north. So 60 degrees east of north. So there that is. You could also look at this as standard form of 30 degrees. Here is another example. We have west of north, so 60 degrees in the westerly direction of north. Here's my 60 degrees, and then here is north, south, west, east. So 60 degrees west of north. Now keep in mind, if you were ever to be given this and you needed to find or calculate the component form, you would not be able to use 60 degrees because this thing right here is not 60 degrees in your calculator's eye. So this is where it's going to take some thought sometimes. So draw a picture of the bearing to seek out standard position angles. So we're going to go ahead and do these examples. Find the component form of a vector with a magnitude or a quantity of 50 in the 60 degrees west of north direction. So we're going to go ahead and look at something like this. Alright, so here's my north, here's my west. Okay, 60 degrees west of north. I'm going to go 60 degrees west of north, and it's going to be at the magnitude of 50, or a quantity. That vector has a force or some sort of quantity of 50. So if I wanted to find the component form of this, what I'm going to have to indicate is, hey, this thing is 90 right here. If I'm going to type this in with that magnitude times and then the cosine of whatever the direction is, comma sine of that direction, I'm no longer able to just simply look at an angle here and say it's 60. So what I'm going to have to do is add that 90 to that 60, and so here's my magnitude. It's 50 times cosine of 150 degrees, comma, sine of 150 degrees. And this is going to end up being that same thing that I just calculated, which is that negative 43.3, comma, and then 25. Okay, so there's the component form of something that took on this direction with that quantity or that magnitude. This one down here, if we had a quantity of 50 and it was the 60, here's my north, here's my east, I want to go east 60 degrees from that north, so it looks something like this. There's 60 degrees, here's 50. Again, we can't just type in 60. To your calculator, 60 would be something up here. So your calculator, we're going to have to take in that this is a complementary angle, that this is going to be 30. So we would have to use 50 times and then cosine of 30 degrees, comma, sine of 30 degrees. Okay, go ahead and give that a whirl. That's going to take care of this objective right here. Translation of bearings to standard position takes some thought. I would most of the time draw pictures. And then finally, find the result by adding butt to head. So remember, if you're ever looking for a resultant of adding two forces together, what you're going to be doing is you're going to be looking at those vectors individually and adding them up together. So let's say that you threw a ball at 50 miles per hour directly north. Okay, so here's that ball. It's directly north. It's 50 miles per hour. And I am going to just draw a coordinate grid here. Okay, so there's my coordinate grid, and I drew it, or I threw, here's my vector that's representing the situation right here. But there was a strong wind with a, sorry, this is horrible. There was a strong wind with a, I should say, force of 25 miles per hour going, 30 degrees west of south. So what we've learned, or what we're considering here, is something where there's two forces at work. So let's combine them. So if you were to look at this, I'm going to go ahead and look at this end result. Okay, that would just have been if I had thrown at 50 miles per hour directly north. But what's happening here is, to this result is another result that I'm going to add on that's combining in this situation. And so I'm going to work with this 30 degrees west of south, and if I did draw a new axis up here, because this vector can start anywhere, remember, what's going to be is south is down here, west is over here, and we want to go 30 degrees west of south. So right here is 30 degrees west of south, and then it's at 20 miles per hour. So our total miles per hour, make sure that they're the same types of vectors combining, our total is going to look at something right here instead. So what I'm actually going to have to do is not only calculate this component form, which is going to be 50, and then it is just a 90-degree angle, so cosine of 90 degree, comma, sine of 90 degree. I'm also going to have to add on to that this vector as well to get what my actual final result was. So it's going to be 20 because that's this quantity of that vector, and then here I have to be careful because I'm not going to use 30. I have to go all the way around. There's 180, and here would be 60, so I'd have to take cosine of 240 degrees, comma, sine of 240 degrees. What I am going to get is this is all equal to, I'm going to take 50 times the cosine of 90, which is going to get me the component form 50, comma, 0. plus I'm going to take 20 times the cosine of 240, which is going to get me negative 10, comma, 20 times the sine of 240, which is going to get me negative 17.32. And when I total this up, I'm going to get 40, comma, negative 17.32 is where I actually ended up. Not at 50, comma 0, but this thing right here.